Okay, one of the standard applications for implicit differentiation is a related rates problem. This is when we have quantities that are related to each other and they change with respect to time, and so they're related to each other in regards to the rates of change with respect to time that they have together. Now, in this example here, sand falls from a conveyor belt at a rate of 10 cubic meters per minute onto the top of a conical pile. The height of the pile is always 3/8 of the base diameter. We are asked to find how fast are the height and the radius changing when the pile is 4 meters high, and our answer is going to be in centimeters per minute. Now, there's a couple of things to highlight here. Number one, alright, we have a rate of change here, alright, and we should highlight it, and this rate of change is this one here, 10 cubic meters per minute. So this is a rate of change of volume, and so since we have a rate of change of volume, let's put this one here. This one would be dV on dt. Okay. Alright, next, alright, it's a conical pile. So we're talking about a cone, and if we're talking about a cone, we should know what the volume of a cone is. And so this would be the volume is equal to 1/3 pi r squared h. Alright, so we have that one. And we have the height of the pile is always 3/8 the diameter. So of course the diameter is 2r. Okay, and so we want 3/8 of 2r, right, which will be 3/4 r. Alright, so that's the radius that we have there, and it says how fast are the height. So if we're looking at how fast the height is changing, we're looking at the rate of change of the height. Let's look at that as dH on dt, and the rate of change of the radius, alright, and that'll be dr on dt. Alright, and when the pile is 4 meters high, so this is the height right here. So we're taking a snapshot of what's happening here. Alright, now it's always wise to draw a picture of this. So let's do that. Alright, so we have a cone. Alright, and so this is our pile. Alright, we have a height and a radius. Alright, so notice that the volume here is now given by 1/3 pi r squared h. Here is the radius, and here is the height. Alright, now we've got things changing with respect to time. Alright, so notice that we do have h here, and we do have the radius. Notice we do also have that the pile's height, that's h, is always equal to is always equal to the 3/8 of the base diameter. Now the base diameter, of course, is all the way across, and so consequently what we need to do here is replace this h. Alright, so h is equal to 3/8, as we said, alright, of the diameter, which is twice the radius. Alright, and so this therefore becomes 3r on 4. So what we have here is 1/3 pi r squared, and now we have 3r on 4. So we now have the volume in terms of the radius alone. We want the rate of change of the height, so we're going to have to look at that shortly, and we want the rate of change of the radius. And now that we have it in the radius form, then we can do that. Now notice that both the volume and the radius are changing with respect to time, so they're related to each other. So we need to simplify this. This will be simply 1 pi r squared on 4, and of course r by r is r squared by r is r cubed. So now we have the volume. So when we do the derivative of this with respect to time, we need to treat this radius as a function of time. So the pi on 4 is a constant, and we do 3 r squared dr on dt. Okay. Alright, so consequently now we have dr under t, which is one of the things we need to find. That's one of the things there. We do know this one, okay, and we do know the radius. Well, do we know the radius? That's a good question. Notice that we have the height of 4 meters. So if we come across here, we need to start thinking about, okay, if when h is equal to 4, this tells me that 4 is equal to 3/4 r, so r is going to be 16 on 3. Okay. Alright, so we now got the radius. So we now substitute. We're going to do 16 on 3 squared, and dr on dt is what we're wanting, and we need to put in now, of course, that the rate of change of the volume is 10. And now our task will be to simply simplify this. So we end up with 10 equals pi on 4 by 3 by 16 squared over 9 dr on dt. So this goes by 3's here. Alright, so we can do 16 by 16, so this will be 10 is equal to, that's 256, so that will be 64, and we end up with 64 pi over 3 by dr on dt. Right, now dr on dt then is going to be equal to 30 over 64 pi, which of course is 15 over 32 pi, and this will be of course in meters per minute with the units. Alright, so that'll be meters per minute. Now of course if we want it in centimeters per minute, then of course there is 100 centimeters in every meter, so this would be 1500 over 32 pi, which of course is going to be 750 over 16 pi, and we can just keep simplifying that until you get an approximate answer. Alright, so that's the method by which we approach this kind of problem. Now what if we want to find dh on dt? Okay, well we have dr on dt, alright, and of course we do have a relationship, and if we come back up here you'll see that we do have a relationship, alright, between the radius and the height, which is right here. Right, so in other words, here's our height. So if we were to differentiate these two, alright, notice that this would imply we'd have 3/4 dr on dt, alright, would be equal to dh on dt. So now that we've got that, we already have just worked this out, multiply it by 3/4 and that'll give us our dh on dt. Alright, so you should make sure you go through the details of that, and also make sure that you do the final calculation here to find dh on dt.